Hello everyone, I hope you all are doing well. So today we will try to learn a different approach to cost elimination, and a very important part of this approach is the process called decomposition. In this particular process, what we do, we split or we decompose our stiffness matrix into three different symmetric matrices, which are namely the L matrix, T matrix, and L dash matrix or L transpose matrix. So we will try to see what are these matrices. The first thing we need to know that this is not different different to gas elimination. It is just the approach is different. That means we are doing everything in the matrix form. So if you remember the Gauss elimination, in the Gauss elimination, in the first step we used to calculate some coefficients like Li1, which is equal to Ki1 by K11, and these coefficients are used so that we can eliminate the uh, all the numbers from the first column, okay, except for the first first number of the first row. So this is in the step 1. That means we had this coefficients, and those coefficients are being used to get the final matrix. The same thing, the process that we have followed can be also represented in matrix form. So in matrix form, if I write those coefficients in this form, so this is a general matrix, where that is why I have written m here. So it, because the matrix size can be different in if I write it in general, so I can write the all the li1 coefficients in this way, right, in the first column of the matrix, and diagonally it will be 1 and all the other elements will be 0. Now let us try to see that whether we can replicate the same thing that we have done in the previous class in the Gauss elimination, uh, by using the matrix method. Okay, so suppose from the previous example we have taken the same K, and here this L1 inverse, suppose this is, I can write it as L1. Suppose I write it as L1, and these are the values of coefficients. Just write it here. Here I should write L21. So I will write 5 by 9. 5 by L1 will be 5 by 9. Then L31 will be 6 by 9 from this equation. Then minus 8 by 9, and others are 1. And if I, the minuses are there, okay, minus are there, minus 2 1, so minus 5 by 9, minus 6 by 9, minus 8 by 9. So if multiply L1 into K, then I will come up with this particular matrix. And as you can see from the previous PDF, that if I use the same, if I use the Gauss elimination, we got that same matrix. Now that means it is possible, by using this kind of multiplication, we can replicate the same step that we have followed in the Gauss elimination. Now similarly, if I move on to the second step of the Gauss elimination, then in the second step we have find out Li2, which are shown in this equation. Then same coefficients we can write in the same format, that is the diagonal elements are 1, and here in the second column I can write minus L32, then minus L42 up to minus L and 1. Okay, and if I do for this problem, this equation, this particular matrix we have got from the previous for the step 1, then from the step 2 this will be what, minus 1.333 divided by 2.444. okay, so in this form we have written the coefficients, and if I multiply this to this new L2 with the previous matrix, that is L2 L1 to K, I will come up with this particular matrix. So as we have taken only 1.333, that means the round off factor error is always will be there, but as this elements or these values are very small, so we can take it as 0. So finally we will get this matrix. So we can see that each step we are getting 0 and 0, that means we are approaching in the Gauss elimination method. Now as you can see, from here L1 inverse and L2 inverse, all matrices we need to multiply in this form. Okay, now suppose if we denote this final upper triangular matrix as S, then we can represent this whole equation as the upper triangular matrix S is equal to L n minus 1 to the means to the inverse, then up to L2 inverse, L1 inverse into K. That means what we are finally approaching to, what is our goal? Our goal is to find out the upper triangular matrix, right? That is what we have done in the Gauss elimination. We have finally converted our matrix to an upper triangulation matrix. So suppose that the final upper triangulation matrix is S, and in all our steps in doing so, we had find out L1, L2, L3, L4 like dot to Ln minus 1. So if I write all this into K, then obviously we are finally going to end up with the final Gauss elimination matrix, that is the upper triangulation matrix S. Now let us see whether we can do it or not. Suppose what is happening here, we are multiplying this two. Now we have already have L1 inverse and L2 inverse. So if I multiply both these matrices, I will get this matrix. That means what is happening here, we are just adding the columns of each one. Suppose for L1 this is the column we got, then for L2 this is the column. That means means if I want to make it general, then what we need to do, we just need to add for all the coefficients for all the steps in this columns. Okay, so this is for L1, this is for L2, this will be L3, then L4, L5, L6, then it will go on. Okay, so that means the final matrix means if I want to combine these L matrices, then we will come up with this particular matrix. That means all the minus L21, L31, L41, then L32, this is for step 2, then step 3, step 4, and finally step n, then n minus 1, then final step n. Okay, this whole matrix means these small matrices, this L1, L2 can be finally represented as L. Okay, L inverse into K. Now if I represent K matrix as this is inverse, so I can bring it to the other side of the equation, then that will be K equal to L into S. Okay, now this is the L matrix, right? So this is 1 1 1, whichever blank side you are looking at, so all those values are 0. So this is 2 1 3 1 2 1 3 1 4 1 like that. From this column is from the first step, this column is from the second step, like that. So this is the final L. Now if I write this particular equation in the form of a matrix, then it can represent it something like this. Here S is the upper triangular matrix, that is the final matrix we are looking for, right? And this is the L matrix and this is the K matrix. Now this upper triangular matrix can also, suppose we can represent it in this manner, like matrix S is equal to matrix D into matrix S bar. So where D is a only diagonal matrix and S bar is a upper triangular matrix, such that DII is equal to SII, where I is equal to 1 2 3. That means D11 is equal to S11, D22 is equal to S22, means S1 S11 S22 S33, these are equal to D11 D22 D33. Okay, and the S bar will be what, this terms will be 1 1 1 and this terms will be there. You will understand when you will look into it. Suppose this one, so this is the first, the L, right, and these two combined is S. Suppose the S matrix we decompose into two, right? One is D into S bar, So this is D. D means only diagonal matrix, and this is the S, upper triangular. So we can represent it K L D S bar. Now the thing is, here K is symmetric matrix. We already know that. S bar must be the transpose of this L matrix. Okay, so finally we can just represent K as L matrix into D matrix into L transpose. Okay, so this is all just theory. You just need to understand how we can decompose one particular symmetric matrix into this form. Okay, this L, D and L transpose. Now the thing is, we want to find out L and D, because L transpose means L and L transpose are same, basically the same thing. So we want to find out the L values, there's L coefficients and D coefficients, that is D11, D22, D33, as well as L21, L31, L4, like that. Okay, all the coefficients of L and D we want to find out. These are our unknowns. K is already known to us, right? So how can we find out those unknowns? Those unknowns can be just simply we can find out by using some equations. And how to find out the equation? We nothing with that, nothing to be done. You just multiply this matrix, and this matrix. Okay, if you multiply, you will come up with certain equations. Okay, suppose if we multiply this whole equations, then if we compare with this this final initial matrix, that is this stiffness matrix, we can derive some equations. So let us see here. This is a software called Wolfram Mathematica. So here you can it's a very strong software. So suppose we consider a 4 by 4 matrix. Okay, so K, I have defined K as K11, K22, K13, K14. So this is the matrix form. In the matrix form, suppose this is the K matrix. Okay, and suppose I have to define the L matrix. Suppose the L matrix here in this software I have defined it by A. So this is A is this L matrix. Okay, and basically the B is a transpose of A, that is L transpose, and D matrix is basically this one. Okay, so let's see the matrix form of this. Matrix form of this. Okay, okay, this is the matrix form. Okay, this is the D matrix, this is basically the L matrix, this is the K matrix. Okay, so we want to find out, so this L and D's are unknown to us, so we want to find out. So how we can find out? We just need to multiply L into D into L transpose. So if I do that, if I multiply, this is A into D into B, if I do that, I will finally get this particular matrix. Okay, D11, D11, L21, D11, L31, D11, L41. Now consider the upper triangle of this matrix and equate to the initial stiffness matrix, such that, suppose what is K33 over here, if I equate it, K33 will be equal to, from this matrix, this is 1 2 K, this should be the K33, right? K33 is D33 plus D11 L31 square plus D22 L32 square. Similarly L43, everything is available. So from this, if I write, say suppose K33 is D33 plus D11, if I write in this equation in this software, suppose K33, I can write it this form, and I can generalize this particular equation. Okay, also D11, so everything can be generalized to find out the DII matrix and L matrix. So if I generalize these equations, so we will get this particular two general equations. Okay, so these equations will help to find out the D matrix, then this equation will help you to find out the L matrix. But as you can see here, this is also this D matrix is already a function of L, and this L is also function of this. So uh, this is means it's interconnected. Okay, so that is why we need to follow a specific order to solve this kind of problems. Now if I we can finally write down the stiffness matrix in this upper triangular matrix. So saying this, then, and if I equate it to the previous equations, previous this equation, then we can finally find out certain equations for a11, a12, a21, a33, a3n, or all these values. We can find out this equation. So from this equation we can directly find out the upper triangular matrix, that we will get for Gauss elimination. Okay, now let us consider a example and try to find out how to decompose it. Okay, so this is the problem. Suppose this is the stiffness matrix. A 6 by 6 matrix is already given to you. Now we want to decompose it. That means we want to find out the L matrix, D matrix, and L transpose. So the first thing, suppose I define this particular matrix as K11. So this term is K11, this term is K12, this one is K13. So I have just defined it over here. Now for I is equal to 1, that means for the first column, okay, for the first column, first thing that I want to find out is the 1 1. Okay, so we have these two general equations. The first thing is d11. So if I put in place of I, if I put 1, so it will be d11 is equal to k11 minus j is equal to 1 to I minus 1. I is 1, so it will be 0. So it's 1 to 0. So it is not possible. So we cannot sum it from 1 to 0. It or any always we can sum it from 1 to 2, 2 to 3, like that, right? So 1 to 0 we can't do. So this whole part will become 0. You can neglect it. So it becomes d11 is equal to k11, right? So d11 k11, this k11 value is already known to us. It is 15150,450. Okay, then L11. Okay, what is L11? L11 value is 1, because you can see over here. Say suppose this matrix, this is L11, this is L21, this is L31, F41, and 1, right? So this is L11 is always 1, L22 is 1, L33 was 1, L44 is 1, L55 is 1, like that. Okay, so diagonal elements of the L matrix is always 1. So L11 is 1, fine. Then L21, if I want to find out, I have to go to this general formula, right? So if I is equal to, for finding out L21, I will be 2, J will be 1. So put the values here. Here if J is equal to 1, it will be 0. So this term obviously will cancel, this term will be 0, and the final equation that will end up with is k21 by d11, and this will give you 0. The value of k21 is 0 here. See, k21 is 0. So again L31 will be same thing, k31 by d11, then L41 is k41 by d11. So everything we can find out. Okay, and what does it give us? This d11, then L11, L21, and L21, L31, 41, 51, 61. This gives you the first column of D matrix as well as the L matrix. Right, see here, this is the first column. First column is L21, 31, 41, and 1, like that, right? So this will give you the first column. So this is the way you have to do. You cannot find out d11, d22 directly. First you have to find d11, then you have to follow this step, then only you can go to the next step, that is finding out d22, then L22, L32, L42, L52, L62, like that. Okay, so for the next column, so we have got the first column. For the next column, say suppose I is equal to d22, you just put in this general formula. So it will be k22 minus d11 L21 square. So you put this value, L21 you have already calculated. So similarly L21 is 0, because you can see over here is a lower triangular matrix. So L21, this is L21, this will obviously be 0. L22 is 1, L32 we have a value. So let's see how can you can find out L32. Yeah, L32 is, you just put the values in this particular general equation. We want to find L32. I is 3, J is 2. So here will be what, uh, 2 2, because J is 2, so it is be 2 2, then 3 2. Here J is 2, so it is 1 to 1. So only one term will come up. So only one term is coming up. So L3 to 2 2, 3 2, L31, L21. So these values are already we have calculated. So we can find out L32, L42, L52, L62. So this will give you the second column. Like that, we can find out the third column, fourth column, fifth column, and sixth column. So finally, we can find out the what is L matrix. L is the diagonal values are one. I've already told you, and the lower triangular values are L21, L31, like that. So if you put this, you will end up with this particular L matrix. Okay. And similarly, the D matrix is basically only diagonal matrix. You can find out either diagonal matrix, and if you multiply, means I want to check it whether I have the process I have followed is correct or not. So if I want to do that, so suppose what is happening here, suppose I want to find out what is L into D into L transpose. L transpose. Okay, I think this should be L transpose. So this is the matrix. So this is same as the K. So I verified it, so that if I minus K, if I do the minus K, it becomes 0. So everything, these values are very small, so it becomes 0. It's a 0 matrix. So I can say that K is, we have done it. We have decomposed the K matrix into three equal symmetric matrices, that is L, D, and L transpose. Okay. And as now we have already find out L and D matrix, D values, we can put the values here in these equations, and we can find out the upper triangular matrix. Okay. So this is for today. If you have any doubt, you can ask me anytime.